He's a member of faculty at TIFR Mumbai and works in computational complexity, algorithms and discrete mathematics and algebraic automata theory. So before joining TIFR, he was a postdoctoral fellow at University of Toronto and the Institute of Advanced Study Princeton. And even before that, he did his PhD from McGill University. So today we'll talk about monotone arithmetic.
Oh, I think. Hello?
Yes.
Sorry, I think on my side things froze. Okay, so is it fine now? Should I begin?
Yeah, you can start.
Okay, yeah, just give me a second. I'm a little. Yeah, let's see. Sorry. Yeah. Okay, so thank you for the invitation and the nice introduction. Yeah, so I guess it's 4 o'clock. It's sort of late in the day, so I wanted to give you sort of a simple talk. I'll try to keep things as simple as possible. There won't be any proofs. Yeah, and yeah, let's see. Okay, so this is joint work. So it's based on set of mostly one work with Rajit Datta, who was at CMI at the time the work was done. Now he's at Goldman Sachs. Utsav Ghoshal, all these two people are students of Partho Mukhopadhyay at CMI and Partho. So I will mostly talk on one paper, and towards the end we'll talk about some interesting thing. Am I audible and is the screen visible?
Yes.
Yeah, okay, thank you. Okay, so let's begin. So the two main questions, sort of defining questions in computational complexity theory, and I may dare say that in all of theoretical computer science, is this P versus NP question, which was formulated in 1971 by Cook, and its arithmetic or algebraic analog, which is Valiant P versus Valiant NP, formulated by Valiant, no surprise there, in 1978. And these are essentially the same sort of questions you all are familiar with. The first one deals with Boolean functions that probably in the crowd more people are used to dealing with. And the second question concerns the computation of formal objects called polynomials, again very important in natural and mathematics, shows up in many parts. And we want to understand whether polynomials can be efficiently computed or not. And these questions have remained open. So the Boolean question, most people would agree, is perhaps a little more difficult than the algebraic question because there's much more structure. I mean, these are polynomials. People have researched on polynomials for almost eternity now, and so there's more mathematics, classical mathematics, that's available and that should be of use. However, both of these questions are currently wide open, as everybody knows. So in today's talk, I will have little to do with Boolean complexity, except that it will keep coming in and out in the form of communication complexity. But the central objects that we want to look at are arithmetic circuits. These are the models of computation for understanding algebraic computation. So let me just give you a simple example of what a circuit is. So a circuit is I'll just keep it informal. It's a directed acyclic graph, and where these nodes, because you want to do arithmetic operations, the nodes are labeled with two kinds. One of them over here, I hope my cursor is visible. This is a plus gate. It's an addition gate, so you have some underlying field which has addition, so it adds the things that come into it. Similarly here. And then there are multiplication gates, okay, which will multiply. And here I will sometimes label this with field constants. So these are indeterminates, variables. And so, this is very naturally computing. This is called the output gate, and these are the input variables. So this circuit is very naturally computing x1 square minus x2 square. So x1 plus x2 times x1 minus x2, and that's just x1 squared minus x2 squared. That's the polynomial p that's being output at the output gate, and that's the result of the computation. So this is the model. And this circuit, it has depth 2, length of the longest path from the root to the leaf. So it has depth 2, and it has size 3 in the sense that there are 3 gates that are being used. Okay, and these are important resources in our computational model. And in this talk, the field, the underlying field of will be always the field of real numbers. Okay, so yeah, unless I say which I won't probably, it's always going to be the field of real numbers. Now, this computational model, first of all, is universal. It can compute everything, every polynomial. And why so? That's quite simple to see. So if I give you a polynomial p, you list it out monomial by monomial. These are some numbers, non-negative integers. And so, this is a monomial with this thing being its coefficient. Is my cursor visible?
Yes, it is.
Yes.
So,
Yes.
thanks. Yeah. So this is a coefficient. And so the sum, this is the whole polynomial, monomial by monomial, and you can compute using this model monomial by monomial. You just, fix, keep reserve one gate, one product gate for each monomial, and then, have a plus gate at the top and just sum them up appropriately with, with in the wires carrying these coefficients. Okay, so this is a very naive way, but it already shows that at least the model is powerful enough to compute every object of interest polynomial. Yeah, and the fanning of this top gate now is just the number of monomials. Now, in depth 2, therefore, we can compute every polynomial where the size of the circuit will be the total number of monomials plus 1. Okay. And let's see this in action. So, for example, if I have the elementary symmetric polynomial, which is a very common polynomial in use of degree d, so you look at all the multilinear monomials of degree d and sum them up. Okay, so there are n choose d many such monomials, and as before, you can compute them easily in depth 2. Now, however, the size of this circuit, the naive circuit, to compute that is n choose d. Now, if d is large, like log n already, then this n choose log n becomes larger than polynomial in n. Okay, and so this, therefore, in depth 2, although you can compute, you may not be able to compute things in polynomial size, polynomial in n, the number of variables. And we want to compute things efficiently, and efficiently would mean, as usual, polynomial in n size. Okay, so this polynomial, the elementary symmetric polynomial of degree d, it's not hard to show that if all you had is depth 2, then you actually cannot do anything better. But if I give you slightly one more depth 3, then suddenly every symmetric polynomial of degree d, as high as it can be, like n by 2, yeah, and yet it can be computed in just polynomial size, just quadratic size, order n square, which is a remarkable fact, and it's not a trivial fact, it's non-trivial. It's a simple but very clever argument due to Benor. And the important point in this for this talk is that although this polynomial has all its coefficients positive, non-negative, right? This computation in depth 3 is clever and uses cancellations. Okay, negative numbers play a very important role for this computation to be carried out, showing that the presence of negations can help you significantly to cut down cost of computation.
Hey, Arkadev, can I ask a question?
Yes.
So, when you say every elementary symmetric polynomial of degree d, what do you mean? There's only one, right?
Oh, sorry, I meant every elementary symmetric polynomial of d, by this I meant for every d.
Ah, okay. In like irrespective of d, this.
Irrespective of d, this can be carried out.
Yeah, because that's
yes.
like.
Yes.
Yeah. Okay.
Yeah. Good point. For every d, this can be carried out, and the size will stay order n square.
Got it.
Okay. All right, so that was one example.
And just to be pedantic and like maybe unnecessary, but so as you increase the depth, does it even become, say, subquadratic? Like, or is this maybe not an interesting question?
No, it's an interesting question for sure. I'm not sure whether this becomes subquadratic, but let me give you one interesting answer. If you do increase the depth, then you, sorry, go ahead.
No, I'm saying yes.
Yeah, if you do increase the depth, then you don't require cancellations anymore. For example, if I allowed you log square in depth, then for every d you can compute it in polynomial size, and you don't need to have any fancy cancellations.
Okay,
so you can do it in a completely monotone way. You're sort of preempting the monotone here. Okay, I'll come back to this point later. Okay.
Great. Okay.
Asking me questions. So that was efficiency 1. Now efficiency 2. Okay. So suppose I look at another polynomial, again very important, very widely in use, called the determinant. So you have an n by n matrix and you are computing its determinant. That's what's written over here. You sum up over all the permutations. And this polynomial, of course, is not a monotone polynomial, because some of the monomials that will appear here will have a negative coefficient, negative number as its coefficient. It's not a polynomial which is monotone, but if you were to compute it again in depth 2, you will require factorial n size. And this is not hard to prove. However, it's a theorem that if you allow much larger depth, let's say log square n, then you can compute it in polynomial n size. And this is a well-known theorem. And the important point again here is that you need very fancy cancellations. Okay. So let me just say one word about what I meant. In the previous slide, I didn't use the word fancy. I said cancellations, and here I'm sort of deliberately using the word fancy. So what's going on? So in this computation, what happens is that if you notice this determinant, the determinant, the monomials are all multilinear. That means every variable, if it appears in a monomial, the highest power of the variable is 1. That's what a multilinear thing, monomial means. So every monomial is multilinear. However, when you compute it so efficiently, the only way we know how to efficiently compute this is when in the intermediate process you generate all kinds of junk, meaning non-multilinear monomials, and then they cancel out magically, because by the end all such non-multilinear monomials have to vanish, and they do vanish. And it's very important that they appear. The only way we know how to accomplish this computation efficiently is by bringing in this non-multilinear cancellations. This is what I mean by fancy cancellations. Okay. In the previous case, just one word here, for the elementary symmetric polynomial, we can get away with less fancy cancellations. We don't need to bring, the whole computation can be carried out multilinearly. Okay, so this is what I mean by fancy cancellations. And there are several algorithms for doing this, and they're all beautiful algorithms, but they all will give rise to this fancy cancellations. So third question, efficiency point, is suppose now I take off, I make it monotone forcefully by just removing the sign from the coefficient vector. Then this is also a very important polynomial called the permanent polynomial. And it has the same number of monomials. Nothing has changed except that I've made the signs go away. Now what happens is the efficient computation that we used to know for the determinant no longer is available to us. Okay, we cannot carry out that. And this is the canonical example that we have of a very hard polynomial, the permanent. The VP versus VNP question can be restated in terms of the permanent versus determinant question. but I don't want to go there right now. So the question is, can I compute the permanent in polynomial size with as much depth as you want? We don't know. The conjecture, the wisdom is that, the general wisdom is that this should be impossible, but we don't know how to prove it. However, if I force you to have no cancellations, which is what I'm going to come to, the central topic of this talk, you carry out the entire computation in a monotone way, then indeed you can prove that the size required would be 2 to the omega n. Okay, and this is an interesting result because I'm allowing you as much depth. And answering Siddharth's question, I told you that when you give yourself more depth, even monotone computations can be interesting. For example, the elementary symmetric polynomial of every degree d can be computed by monotone circuits of large depth. Okay, so they can do interesting things, but for this permanent, we do know that they cannot compute it in sub-exponential size.
So another quick question for you. So this theorem that you just stated,
yes,
that was for the permanent. Do we have something similar for the determinant?
But you have to be careful in saying how, because monotone computations just cannot compute the determinant because the determinant is not a
right.
But you can make, there are monotone polynomials which are projections of determinants, very close to determinant in spirit in some sense. For them you can prove that monotone circuits require exponential size.
And the point is still, like, while you are looking at cancellations, you're still staying in the same field. Like, you're never going to a field extension, even for the
no, actually this lower bound goes through for whatever field extension you want. That's not going to help you.
Okay.
Because it's monotone. There's no cancellation that can happen, right? I'm the lower that I'm proving is the one that's stated in this theorem is one that does not allow cancellation.
Okay, I see. So yeah, extending it won't help. Okay,
extending trivially won't help. Yeah. So this motivates the definition. So my polynomial is monotone, and as I said in this talk, I'm going to stay with the field of real numbers. Okay. The coefficients are non-negative. So if my polynomial has every coefficient non-negative, then I call it a monotone polynomial. Okay, and a monotone circuit is one where there is no subtraction or no cancellation, no negative numbers involved. So once a monomial appears, there's no way you can take that off. Once it enters into some computation somewhere, it will continue to remain. So this is what makes it weak. And monotone VP is this class of all monotone polynomials that have poly-size monotone circuits. Okay, so for example, the permanent, the previous theorem in this language shows that the permanent is not in monotone VP. Okay. Now, the monotone model has been quite successful in the sense of for proving lower bounds. We seem to know a lot about it. In particular, this is a folklore result now, a very classic result due to Jerrum and Snir from 79, which shows that this result that I just showed you, the permanent is not in monotone VP. This is exactly the result I showed you. And, the analogous result, so although I'll talk about arithmetic circuits from time to time, I'll show you what is known analogously in the Boolean world. The famous result of Razborov showed that a function, monotone function like click, is not in monotone P. I don't want to delve too much into Boolean complexity due to lack of time, but this result is way more delicate combinatorially, again reinforcing the idea that it should be a lot easier to prove lower bounds in the algebraic world than in the Boolean world. There are many other successes. Yeah, the one question that I am interested in this talk is, the power of negation. Okay, so how helpful is negation? Yeah, although I want to compute a monotone function, if I could show that, or a monotone polynomial, if I could show that cancellations cannot help me beyond a certain point, then of course monotone lower bound should lead to general arithmetic lower bounds or general computation lower bounds. So thus this question is very naturally motivated. How powerful is negation? Yeah. And again, this has been answered in both in the monotone, both in the Boolean world and in the algebraic world. Valiant, particularly in the algebraic world, let me focus. Valiant in 1979 showed, there are some polynomials which are obtained by, which are called matching polynomials. So these are, each monomial in some sense corresponds to a perfect matching of a planar graph. Okay, so these polynomials, if the graph is planar, the matching polynomial is in VP. Now this is an example that is close to what Siddharth was asking. This is the matching polynomial is in VP because we can write it as a projection of the determinant if the graph is a planar graph. Okay, and so even though the matching polynomial is monotone, the efficient computation that we know of uses cancellation. In particular, uses determinantal cancellation. Okay, and what Valiant showed was that there are planar graphs for which the matching polynomial cannot be computed in polynomial size by monotone circuits, thereby giving an exponential gap in power between monotone computations and non-monotone computations. So this is a very early result, 1979. Yeah, Razborov showed the same in 1985. So you may ask, like, what is there more to know about the power of negation? Because we have.
Hey, Arkadev.
Yes.
Yeah, sorry, I keep bothering you, but
No.
Yeah. So you said, yeah. So this is quite interesting. So, but you say it's exponential, but like it's still like let's just look at the matching polynomial. So it still doesn't rule out like a monotone but quasi-poly-sized.
No, it does. It does, because you mean by monotone, because the lower bound that Valiant proved was 2 to the omega root n.
Okay. So MVP is like is
Yes, MVP, yeah. It's not expressing the full strength of Valiant's result.
Okay, got it. Okay. Yeah, so it's MV sub X per something.
Yes, yeah. And not only is it not an MVP, the every monotone circuit computing the matching polynomial would require 2 to the omega root n size. Okay. So right. So that's what I meant by an exponential gap. So it was demonstrated very early on by Valiant in 1979. Now, what is there more to know? Well, here's a mystery that sort of, I find quite interesting, which is the following. I want to understand it even more. I want to push this question to the extreme. I want the simplest model of general computation. By general, I mean a computation that has access to cancellations and negations. So I want the simplest model that is still exponentially more powerful than the most unrestricted monotone model. Okay, so I want to be able to compute a monotone polynomial having access to negations in as simple a fashion as I can, and yet prove that even if you give an all-powerful monotone circuit, no restriction on depth, nothing, it still finds it hard to compute it. Yeah. And another way to phrase this is like, I want my cancellations to be in the simplest possible kind of cancellations. Yeah. And as I said, Valiant's result, sorry, somebody is requesting control. I see Aditya Subramaniam is requesting control. Allow, deny, stop presenting. What should I do?
Sorry, that's a mistake. Sorry, that happened by mistake.
So I should ignore it or should I deny it? Let me deny it. Yeah. Okay. So yeah. So the question is, I want the simplest kind of cancellation. Yeah. In particular, Valiant's result showed that here's a polynomial, the matching polynomial for planar graphs, but it requires determinantal cancellation. In other words, although the target polynomial is not only monotone but multilinear, the cancellations have to bring in this weird determinantal thing. All kinds of monomials will appear and then disappear. So in particular, here, sorry, why is this? Okay, so something has happened. It has. Can you hear me still?
Yes, sir. I think
Yes.
there's a nagging thing.
Ah,
okay.
Okay.
Vanished now.
Now it's vanished. Yeah. All right. So what I meant by this is sort of multilinear cancellations. Okay. So these are cancellations where these are way more limited cancellations than determinant cancellations. In particular, can you show that multilinear cancellations are more powerful than monotone? Okay. This was not answered by Valiant, and it turns out that this was not answered until very recently. Okay, so another way to rephrase this question is the following. Suppose my circuits, the general circuits, was just a formula. It was not even a circuit. Are general formulas more powerful than monotone circuits? Okay. Another question could be, suppose I gave you, forget general formulas, I give you constant depth formulas, of course with cancellations, but they are constant depth. Are they more powerful than monotone circuits for computing monotone polynomials? Again, by monotone circuits, the depth is unrestricted. The only restriction is the circuit is monotone. And it turns out, interestingly, that all these questions were open, both in the Boolean world and in the algebraic world. These are still open in the Boolean world. Okay, and it was open until our work in the algebraic world, and the main result that I'm going to talk about today is a resolution of this question, this series of questions. You will see several of these questions get resolved by a single result in the algebraic circuit. The Boolean question is still wide open. Okay. So
Arkadev, when you say you're only allowing like multilinear cancellations, is that equivalent to saying that you're always going to compute multilinear expressions?
exactly.
Never.
Exactly.
Okay.
Yeah. So
Okay.
every intermediate gate, the output
Right.
of it is a multilinear polynomial.
Okay. So that's your model, which is stronger than the MVP, say, or the
Yes,
the monotone one, but still more structured than an arbitrary one, which would look at higher degree monomials.
Right. So it is seemingly stronger until
Right.
our work. It was not known to be stronger.
Okay. Okay. Yeah. Seemingly stronger.
It's seemingly stronger. I mean, of course, we have to compare apples to apples. So we only compare the power of these two models insofar as monotone polynomials are concerned, right? Because monotone guy cannot compare anything non-monotone. Yeah,
right.
You have to give it something that it can compute. And then in the context of monotone polynomials, until our work, it was not known whether multilinear circuits had any edge, super polynomial edge over general monotone circuits.
Okay, got it.
It was not even known whether multilinear formulas had edge. Yeah. And what we will show is that you will see in a moment. Yeah. So here's our result, and it can be thought of as a new result on the power of cancellations. So I'm going to show you some polynomial, yeah, whose degree is about square root of n. Here I have used capital N. Sorry, excuse me for that. This is the number of variables, and this I'm going to ignore log factors. Okay, so that's what I mean by this. Such that this polynomial can be computed by an extremely simple circuit, depth 3 multilinear formula. So it's multilinear depth 3, okay, and of very small size, order n to the power 2.5, just above quadratic. But every monotone circuit, this is a monotone polynomial P, obviously. So every monotone circuit, that's the monotone complexity of this, is exponential in the sense that it's, again, in the exponent you have n to the 1/4, give or take some log factors. Okay, that's the result. And this result, the first remark is that, well, it answers all the three questions that I listed before because it's a constant depth circuit. It's multilinear. Okay, and it's a formula. Okay, anyway, with constant depth, everything can be made into a formula. So, in one shot, this answers all the three questions. And the result is optimal in the following sense. In what sense? In the depth sense that, if you gave me only depth 2, then it's not hard. It's an exercise to show that, they cannot have any power using cancellation. Basically, you are forced to compute monomial by monomial. Okay. you can't do anything better. But depth 3 already has interesting power. We saw that, in depth 3, using multilinear cancellations, you can actually compute every symmetric polynomial. But symmetric polynomials could also be computed by monotone circuits when they were given any amount of depth, log square n depth. Yeah. Here we are showing, however, that this particular polynomial, that we come up with, no matter how much depth you give, monotone circuits will always require exponential size. So in this sense, our result is optimal in terms of depth. Any question? Let me see how I'm doing with respect to time. Okay, that's the main result.
And like, okay, then I thought when you said optimal, you meant that there are some constructions where you can like get slightly better in the capital N exponent, but that's also maybe that's just a very sort of.
No, that's a very good question. That's a very good question. We don't know. Huh? So whether this is optimal, whether there are, I mean, can you make this even stronger? Can you make it all the way go to omega n?
Right.
I don't know. That's a great question.
Okay.
Yeah, this is unresolved.
But yeah, still a huge gap nonetheless.
Yeah. The rest of the talk, I'm going to talk about, how do you find this polynomial p, and how do we prove such a lower bound for p? Okay. Now, the point is, in previous works, as I said, cancellations were of two types, either the Benor kind of cancellations with multilinear or the determinantal. The determinantal is not going to help us because we want to avoid determinantal cancellations, because it's very unlikely that the determinant can be computed in constant depth. Yeah, so they are of no use. And we want to, if you set your eyes on having multilinear cancellations, again, it seems like determinant cannot be computed, although it's an open question. It seems determinant is unlikely to be computable using multilinear cancellations efficiently. Yeah, so we have to find some new kind of polynomial. Yeah, and the point is communication complexity, at least to us, entered into the game pretty unexpectedly here. Okay. And this will take me into a slight back into the Boolean world for a moment, and we will try to understand the power of negation in communication complexity. It will turn out that the central conjectures of communication complexity are also about the power of negation. Okay, and that's the link between arithmetic and communication complexity, as we will see. So for those of you,
before you sort of move on,
yes.
So like if you, so your result is strong in the sense that you actually give me an explicit polynomial, but counting arguments won't help here. In the sense that if I count the number of depth 3 circuits with multilinear cancellations, that the counting. Because maybe you're dealing with reals and so, but maybe with finite fields.
Not just the question of reals. For example, if you go to the Boolean world, these counting arguments we don't know how to use counting arguments to give this kind of separations. Because you want the function, I mean, you can do some sophisticated probabilistic argument perhaps, yet unknown, but it's going to be sophisticated somewhat because you have, at the end of the day, you have to come up with a function or a polynomial that is computable by depth 3 circuits.
Okay.
Yeah, but in some sense, ask me at the end of the talk this question, this whole thing, so you can show that, in fact, our result shows that potentially a random depth 3 circuit computes such polynomials.
Okay.
Okay, in some sense, we can talk about this after my talk.
Great. Okay. Yeah, I'll wait.
Okay, so here's deterministic communication complexity. I won't get into it too much because we will take a certain matrix theoretic view of communication complexity to link it up with arithmetic circuits. But Here's the funny looking model that Yao introduced, and you all know about it. I'll just remind you that this is a very basic model where there are two supercomputers, Alice and Bob. They do not see each other's input. They only get to see their input. Alice gets to see X, Bob gets to see Y, and they want to compute some function that unfortunately depends on both variables, X and Y. And the question is, how many bits do they need to communicate with each other in the worst case to be able to compute this function? And trivially, everything can be computed in n+1. Yeah. And, this looks anything but, how is it even related to computation? Because Alice and Bob are supercomputers. So this seems totally information theoretic. Yeah. And, but it is got all sorts of connections, unexpected connections to VLSI, distributed computing, data structures, so on, blah, blah, blah. Many open problems. By now, it's a very rich mathematical theory. There are interesting books that you can read and should read. Yeah, and however, it turns out that a very basic problem, communication complexity, this communication game appears in so many computing scenarios that this quantity, the communication complexity of a function, is a very basic quantity, right? And yet, a very fundamental and basic question has not yet been answered, which is this quantity combinatorial? Is this quantity information theoretic, or is this algebraic? Mathematically, what is the flavor of this quantity? This is the most basic question, and we don't know. And you might ask me, what is algebraic about it, right? Well, you can actually make a little matrix out of everything, and so here also you do that. You can make a matrix where the set of rows of this matrix are all the possible inputs that Alice could have, and the set of columns are all the possible inputs that Bob could have, and we call this matrix M of F. And the first few lectures of communication complexity shows that the rank enters, the linear algebraic rank of a matrix, is upper bounded by this quantity 2 to the deterministic communication complexity of F. So in other words, if you have a good lower bound on the rank, the linear algebraic rank of this matrix, of this Boolean matrix, this matrix is Boolean because each of its entries is 0, 1, depending on what the Boolean function F evaluates to. So the log of this rank over any field, but we will only look at the real field, is a lower bound on the deterministic communication complexity. Okay, and that's the way rank enters. And here's this very simple looking question posed by Lovas and Sax from 1988, which says that, does rank essentially characterize communication complexity? Meaning that, well, the lower bound is not too far from an upper bound. There exists some universal constant alpha, such that the deterministic communication complexity of F is also upper bounded by a fixed exponent alpha raised to the log rank of F. So a polynomial in the log rank with a fixed exponent. There's a universal constant alpha, right? And this is notorious conjecture called the log-rank conjecture. This is wide open. Every student of theoretical computer science should waste some time on this problem, I feel. It's such a basic and important problem. And what has this got to do with what we were interested in? It looks like I'm going on a tangent here. But it turns out that this question is a fundamental question about negations. And here's how it is. Here's the matrix theoretic view of the Lovas-Sax conjecture, also widely known, is that you take this matrix M, the communication matrix, and now basically look at any Boolean matrix. So the Lovas-Sax conjecture is equivalent to the following assertion, that if I take any Boolean matrix M, my field is again the reals, but my matrix entries are now filled with zeros and ones, then the log of the non-negative rank of this matrix is upper bounded by the log of the ordinary linear algebraic rank raised to the power some fixed constant alpha. Yeah? This is equivalent to the log-rank conjecture. Okay, this is totally communication has gone out. This is the matrix theoretic view. Okay, and by non-negative rank, what do I mean? You take the matrix M, you decompose it as you do for the case of rank as a sum of rank 1 matrices, but those rank 1 matrices must have non-negative entries, no cancellations. So what this conjecture is saying is that the non-negative rank is not too much larger than the ordinary rank when you scale things down logarithmically. Okay, so it's basically saying that negations are not of much use when you want to compute matrices in this way. Okay, so it's exactly saying that the power of negation is limited, quantified in this way. Okay, and this is wide open. Okay, and this conjecture, as you can see, stripped off all pretense of communication and computer science, is a fundamental mathematical conjecture about matrices. Okay. And here's so how am I doing with time? Yeah. Okay, so here's a different generalization of this conjecture. You know, why should we care about Boolean matrices? What happens, suppose, you know, I look at these matrices, but these matrices are no longer Boolean, but they're almost Boolean. They're epsilon approximately Boolean. What this means is that every entry of my matrix M is epsilon close to being either 0 or 1. So, you know, if you draw an epsilon ball centered around 0 or 1, you know, my entry is there. Every entry has this feature. So if I look at such an approximately Boolean matrix, this conjecture due to Troy Lee and Adi Schreibman from 2007 can be recast. This was said in a communication complexity language, but it can be recast in this language, where it says that the non-negative rank of approximately Boolean matrices cannot be too much larger than their ordinary linear algebraic rank over the reals. Okay, and this is basically saying what an approximately Boolean matrix is. Again, this is a purely analytic or algebraic conjecture, nothing to do, I mean, you know, general mathematical conjecture. So these two things seem very close, except one is Boolean and the other is approximately Boolean. And it turns out that this conjecture, the more general sounding conjecture, is unfortunately false. And this was a counterexample that we came up with in joint work with Nikhil Mande and Suhail Sharif, both students at TIFR at the time, where we were able to demonstrate an approximately Boolean matrix whose you know, non-negative rank is way larger than its ordinary rank. In particular, you know, the log of the non-negative rank is exponentially larger than the log of the ordinary rank. Okay. And therefore, if you have approximately Boolean matrices, then it seems that negations do help you enormously. Okay, so in particular, you know, if you look at quantitatively, if I had you know, n by n, sorry, 2 to the n by 2 to the n matrix, the log of this rank, non-negative rank, is omega root n. This matrix will have really small, sorry, this will have, the log of this will have really large rank, because if you take away the log, this non-negative rank is exponential in n, 2 to the root n. However, the ordinary rank is polynomial in n. Yeah, just polynomial. So the log would be log of n. So that's the exponential separation. And this shows that even though we don't know for Boolean matrices, for approximately Boolean matrices, negations help you widely. Very significant. Okay. And so this is one example, one concrete example where we see that the power of negations can be significant. Okay. Now, what's this got to do with our question in circuits, except that, you know, both are talking about negations? Well, it turns out, you know, there's a very close correspondence here. To do that, let me take the language of set multilinear polynomials. These are polynomials, if you have tuned yourself to the theoretical computer science or complexity theory news, these are very much in fashion now. There's a breakthrough work of Limay et al., which used the set multilinear polynomials very recently. It was crucial, and again, we will take recourse to set multilinear polynomials. So what are these objects? These are very special kind of multilinear polynomials. Okay. And the connection to communication complexity would be very clear once we focus on this set multilinear polynomials. It will be particularly convenient. So to define this, let's look at our set of variables, and these set of variables are sort of divided up in buckets. So, there are n buckets or n blocks, yeah, and each block contains m variables, or each bucket contains m variables. Okay, and I've used this double index to access these variables, and every monomial, a set multilinear monomial would be a monomial that would take exactly one variable from each block. Yeah, it will wiggle its way. It can take one variable from each block and exactly one. Okay, so every monomial would be of degree n, taking exactly one variable from each block. And another way to define this would be like, I have some map, sigma, which is mapping each row to its some column, yeah, from n to n. Okay. And a multilinear monomial corresponding to this map is exactly this thing, yeah, x I sigma I. Take I, wherever sigma map to I, take that variable. Yeah, so I was here, so you take a particular variable from here, which is given by sigma, and so exactly you have degree n. It's multilinear, precisely taking exactly one variable from each row or from each block. Yeah, that's a multilinear monomial. And a multilinear polynomial is just a sum of multilinear monomials. Okay, and notice that many of the familiar polynomials that I talked about, the permanent, the determinant, the iterated matrix multiplication, which has again been on the news, spanning tree, matching polynomials, these are all set multilinear polynomials. Yeah, so arithmetic circuit literature abounds in set multilinear polynomials. Okay. All right, so let's stay with the set multilinear polynomial. Now suppose I want to tell you what's the connection to communication complexity. So suppose there's a monotone arithmetic circuit that's computing a set multilinear polynomial, then there's a very interesting structure theorem, which is folklore, I think usually attributed to Hayafel. Now suppose P is such a set multilinear polynomial which has a monotone circuit of size S. This gives a structure theorem. Just as a communication protocol, you can decompose it into a sum of rectangles or submatrices. A very nice thing happens with monotone circuits is the following, that if you give me a polynomial P with a monotone complexity of size at most S, then it decomposes in a nice way into a sum of simple polynomials, where each of the simple polynomial is a product polynomial. And what do I mean by a product polynomial? Well, remember my input variables were arranged in this matrix form or this bucket form, right? Now, if I look at this alpha I comes with its own set of rows, which I am calling it as IA. So this is one set. These blue things are the set of rows which alpha I depends on. So it's alpha I itself is a set multilinear polynomial on the blue rows. Okay, and beta I, this is not the, I'm sorry, I just went colorblind here. Sorry, this is whatever, this color, yellow or golden color. Okay, alpha I depends on this set of rows, and beta I depends on the set of blue rows. Okay, so alpha I, beta I, they induce a partition of the rows of my variables, with alpha I only depending on one set of rows and beta I depending on the complement set of rows. Okay, but every alpha I, beta I makes its own partition, and you can and these are called product polynomials. So alpha I only depends on these set of, this set of rows, and beta I depends on these set of rows, and then you take the product. Yeah. And not only that, this thing, you can forget this, it's sort of a balanced partition. Alpha, none of these parts are too small. Okay, that's a technical aspect. So it's a sort of a balanced partition. Ray, ask me a question if something is unclear, right? We are, yeah.
So this cannot be repeated. I can't apply the structure theorem on alpha I and beta I again. I can't.
Can you? Yeah, you can actually, you can, but we won't.
Okay. So like you don't want to like do it like a log depth where keep on shrinking the.
You can, and people have done in other contexts, but today we are not going to do that.
Okay.
Good question.
But this is like again, maybe I'm just guessing here. This looks like a non-negative rank kind of.
It looks like a non-negative rank, but since you asked it, it's exactly, that's the connection, but with a very important difference. The important difference is, as I told you, this partition depends on I. So alpha 1, beta 1 induced one partition, right?
Okay.
I'll explain you. Let's go to the next slide and you will see with a very important difference. Yeah. Here's the caveat, right? And that's exactly answering Siddharth's question, which is that, this choice of IA and IB, they will vary. So alpha I, beta I induced an IA, IB, alpha J, beta J induced a totally different JA, JB on which I have no control, right? Now, which matrix? See, there are two matrices here. Don't get confused by this. This matrix is the sort of bucketing structure of the variables themselves. The thing that you want to look at is this what's called the partial derivative matrix, for a fancy name, but the matrix is this very simple, right? Look at alpha I, it's a vector written in this column form, and beta I is a vector, the coefficient vector written in this row form. And you're taking the outer product of these two, right? That's what Siddharth was alluding to when he said that it looks like rank 1. Yeah. Now this is alpha I. It's got a coefficient vector over all monomials that come from this IA, the set of rows in IA, right? Multilinear monomials from the set of rows in IA, and beta I is a coefficient vector whose coefficients come from all the set of monomials, multilinear monomials coming from the rows indexed by IB. Yeah. This is a very long matrix, a vector, and this is a very long vector. Yeah, this is not of the size of IA. You look at all multilinear monomials that come from IA and all multilinear monomials that come from IB, and these are the coefficient vectors, and then you take an outer product and you form a matrix. And as Siddharth said, because alpha I and beta I, these are, sorry, I forgot to say, they have all these coefficients are non-negative. This looks like a rank 1 decomposition, not just that, but a non-negative rank 1 decomposition, but with respect to this particular way of defining the matrix, right, for this IAIB, right? And this is exactly what Siddharth was alluding to, and I just said that, right? This is a non-negative rank, but non-negative rank, this is why I put this subscript IA, IB. When I go to alpha J, beta J, that's of rank 1, but not with respect to the same partition, right? And when you sum them up, you don't know. I mean, you can't now apply the simple subadditivity of rank, because the subadditivity of rank is when you have a matrix, right? A polynomial is just a vector, and when I'm taking a product polynomial, each product polynomial is viewing it as a matrix, with its own partition. So if I sum up two such product polynomials, I cannot say that the non-negative rank with respect, I mean, it doesn't even make sense. What do I say? What do I mean by the non-negative rank when I sum up two such totally different kind of things with their own partitions? Does that answer your question, Siddharth?
Yes, I see the, I see the point, like these partition, like the change of IAs and IBs kind of, they're different representations, but yeah.
And this is at the heart of arithmetic complexity. This is what makes circuits much more complicated than communication. Okay, this is at the heart of it. I mean, we don't understand what happens when you change partitions, and if you did, several important problems would be solved. Okay, in arithmetic complexity. Okay, so yeah, and I just wanted to point out one thing. Even if I allowed cancellations, this theorem is very general. Suppose I had a multilinear computation. This is good to know for your culture, that you can actually write it again as a sum of product polynomials. Two things will go away, yeah, which is that this will no longer be a non-negative vector, alpha I, and beta I again will not be non-negative vector, and therefore, you won't be able to say that this is, even with respect to this partition, the non-negative rank is 1, but the ordinary rank will be 1. Yeah. So this structure theorem that I alluded to for monotone carries over to multilinear once you take away the non-negative part, right? Okay. Again, when I add two such things, I won't be able to say that the ordinary rank is at most 2, because the two things have their own partition. It doesn't make sense. Yeah. And this is a very interesting thing that I haven't talked about before. While preparing this talk, it came to my this question popped into my mind, which is, you can have a multi-partition log-rank conjecture. Yeah, because if you take the mathematical or matrix theoretic view of the log-rank conjecture, at this point you can ask this question, which is intimately connected between the power of multilinear circuits and monotone circuits. We can be formulated in the following way, whether just exactly the log-rank conjecture, but now I want to introduce this word multi-rank. Right now, multi-rank. Sorry, here's a problem. This should not be M. Wherever you see M, please read it as P. Okay. So what do I mean by multi-rank? Multi-rank is like, I've been given a polynomial which is just a vector, not a matrix. Right now, you take this polynomial and you want to write it as a sum of product polynomials. Yeah, in non-negative fashion. Yeah. And the number of things that you require, yeah, is, I define it to be the multi-partition non-negative rank of this vector. Yeah. And when you allow cancellations, then I just call it the ordinary multi-rank. And so you can have a multi-partition log-rank conjecture which asserts that there exists a universal constant, is very totally, inspired by the log-rank conjecture, saying, in the multi-partition world, you again have a similar phenomena that if you have a Boolean polynomial, meaning the polynomial's coefficient vector is only having zeros and ones, then negation should not help you much in this sense. Okay, and this is intimately connected to saying that, if you have a Boolean polynomial, multilinear cancellations cannot help you in computing monotone, in computing the polynomial as compared to monotone computations. This is totally open. Okay, this is not known yet. And you can also talk about approximately Boolean polynomials, right? Just as we did in the log-rank conjecture. And then it turns out, and we can cast our main result, the mathematical core of our result is up in this slide. Okay. Yeah, stripped of its circuit, etc. This is the result that we prove, which is that, just as the log-approximate-rank conjecture failed for matrices, the approximate version of the multi-partition log-rank conjecture fails miserably for approximately Boolean polynomials. Yeah, so we find out a polynomial P, which can be written if you allow product polynomials with negative coefficients very efficiently, but if you only insist on the product polynomials to have non-negative coefficients, then you require a large number of such product polynomials to sum it up to the polynomial P. Okay, this is the essence of the result. I'll just pause here for this to sink in, and if you have any question, so I just named it as multi-rank. As I said, this is something that I came up while preparing the slides. So this has not been presented in any way. So this is the premiere of this version. So if you have any questions, please ask.
Can you speak to some, like, how do you identify such a P? Is this similar to?
Yes. So okay. So let me say something here. It's worth noting. I forgot to state one thing. It's a very strong refutation. I'll come to that. How to find P in a moment. Notice that here I have not said multi-rank. I've just said rank. Right? and here I've said multirank. This is deliberate. Why? Because this polynomial P will turn out to be such that, you know, there is a fixed partition. In fact, all partitions will work, all balanced partitions will work. Fix your partition, and it will turn out with respect to that partition, the ordinary rank will be small. But even if you allow decompositions where you change your partitions, but you stay non-negative, this is not going to help. Okay. Now, this polynomial P, we are going to find from the counter example to the log-approximate-rank conjecture. There's an encoding. We are going to precisely use the encoding of a Boolean function that was found out in the context of the log-approximate-rank conjecture counter example, and cook up the polynomial. Okay, and that polynomial will witness this separation. Okay. Okay, so and let me tell you how to do this, and this will show you how to sort of, given Boolean functions, how to manufacture polynomials. So again, we are going to stay with set multilinear polynomials. So take a set multilinear monomial like this, corresponding to a map, and now I define what is called a parity vector of this monomial. The parity vector is just going to be this thing, which is, I take the map sigma, look at its pre-image, the pre-image of 1, column 1, its cardinality mod 2. That's the first coordinate. The second coordinate is the cardinality of the pre-image of column 2, mod 2, and so on. Here's a quick example which will make it completely clear. Suppose I had this monomial where n was 4 and m, the number of columns, was also 4. And this is my monomial. This is you can see this is a set multilinear monomial, right? What is its parity vector? Well, in the first coordinate, let us look at the pre-image of 1. There's only exactly one pre-image. 1 has the pre-image 4. Nothing else got mapped to 1. So the parity is 1. Well, if you look at the second column, nothing was mapped to the second column. So the cardinality is 0 and mod 2 is 0. For 3, 2 things got mapped to 3, 1 and 3. So again, it's even. So the parity vector here will have 0. And 4 has again 1 guy, so it's 1. So that's the parity vector. I hope the parity vector concept is clear. Right? So given a monomial, I look at its parity vector, which is a Boolean string by definition. Right? And here's now a way to manufacture polynomials. Okay, so in fact, take any function f, which is the domain is Boolean, but it's, it could output any real value, assuming that it outputs non-negative value. And here's a way to make a polynomial out of it, set multilinear polynomial. How do I do that? Well, this is the polynomial, its coefficient. Give me a monomial. What is its coefficient going to be? First of all, I want it to be set multilinear. So if it's not set multilinear, I assign 0. This is just to make the polynomial p superscript f set multilinear. And if it is a set multilinear monomial, then I look at its parity vector and I look at the evaluation of f on this parity vector. This, remember, is a Boolean string, right? So this gives me the value, the coefficient of this monomial in this polynomial. Yeah, and this will always create a set multilinear monotone polynomial because my f was that. Moreover, if f was a Boolean function, then this will always create Boolean polynomials, 0-1 polynomials with 0-1 coefficients. And the hope here, the idea is that although this is an algebraic object, p superscript f, I'm going to look at the combinatorial or analytic properties of my Boolean or real valued function f to say something about the algebraic hardness of p superscript f. Yeah, we will make this correspondence. Our work is just building this correspondence between the combinatorial analytic properties of f to the algebraic hardness of p superscript f. Okay. And what f should we use? Of course, given this setup, the first thing is, well, because of this LARC was a refutation of the, LARC showed the power of negation. So, why don't we use the same f? And it turns out that that f can be used. And I don't want to go into the description of this f because I think, how much time do I have? I think I'm almost out of time, right?
Yes, but I think we can still continue for 5 more minutes.
5 more minutes. So let me skip because some of you have seen this. It's a very interesting example, the sync function that was used for LARC. The point is the following. So it's some function that was defined based on graphs, totally combinatorially Boolean function. And it turns out that we can exploit sync. So for the moment, just assume that sync is some function. I want to only show you the correspondence between arithmetic complexity and communication complexity. At the moment, sync is some black box function. Yeah, it's a very natural, simple function. But here's the thing. Yeah, what we're going to do is, well, we need one more definition. So suppose I have a Boolean function f. I'm going to say that g is epsilon approximate to this f. If g is not Boolean, but g is pointwise approximating f well, it's within epsilon. It's approximately Boolean, right? Moreover, at every point, g's domain is still Boolean, 0, 1 to the n, but at every point, g evaluates epsilon close to what f evaluated to, right? It's in this sense a pointwise approximation of f. And here's the theorem. What we can show is that there exists some such g, yeah, which is a close approximant to the complement of this sync function. So this function comes from the refutation of the Log-Approximate-Rank Conjecture, such that when you look at p raised to the g, this has poly-size depth 3 circuits. So this is something we need to prove. I won't have time to prove it. And this uses epsilon bias spaces. So it uses cancellations using some objects called epsilon bias spaces. You use epsilon bias spaces to show that this will actually, using multilinear cancellations, lie in depth 3. Yeah, very importantly, p superscript g will not be Boolean. It will be approximately Boolean. Okay, because g is approximately Boolean. And the second result is a lower bound. It shows that for every g which is close to this Boolean non-sync, yeah, the monotone complexity of p to the g is going to be exponential. So there are two results. The first uses epsilon bias space to give you an upper bound on the complexity of p to the g using cancellations, multilinear cancellations. The second result shows that no matter what g you choose, as soon as it starts approximating f, p to the g is very hard without cancellations. The two combined together gives you what you want, right? You get a polynomial which is in depth 3 poly-size formula, multilinear formula, but no monotone circuits of sub-exponential size, of let's say quasi-polynomial or whatever, right? You need 2 to the omega into the 1/4. That's the result, okay? And again, since I'm sort of running out, I just want to tell you, okay, so the upper bound, I'll not have time. It's not hard. Once you see the idea, it's quite simple. I want to just tell you about some complexity measures for those of you who are interested in proving lower bounds in arithmetic complexity. What happens is that, this is the communication complexity setup where you have a function f and you have x and y, and you can look at this. This is a particular instantiation of the communication complexity setup where you do the bitwise XOR of x and y and then apply f to it. Yeah, that's the communication complexity. And here's the matrix. Yeah, this is the XOR matrix. These are called XOR functions because you XOR bitwise this thing. And this is the communication matrix. Yeah, and what we have done is, there are well-known complexity measures that were used in communication complexity, like corruption, discrepancy. These are very nice complexity measures. I won't be able to get into them much. What we did was we showed that whenever some measure that's called the corruption measure, informally this is what we showed, is that whenever the corruption measure is high for this matrix, then a very analogous measure which tracks, arithmetic computation, which is like a corruption measure. This lifts to a certain measure being high for these polynomials, p superscript f. Yeah, this is, so it's sort of giving a one-to-one, or in one direction, not one-to, I mean from communication complexity, from matrices to the set of monomials, I mean to the polynomial space. So it's translating this corruption measure from the from communication complexity to arithmetic world. Okay, and that's how we achieve this. It's a new measure, and let me take just 2 more slides because I want to introduce a conjecture that I haven't talked about before anywhere so far, which is, there's some measure called the discrepancy measure. So now it might seem I'm going into a tangent. Just bear with me for 2 more minutes. I think it's an interesting conjecture. So a discrepancy, so this is just simple thing. Discrepancy again is very useful in algorithms. There's something called discrepancy theory. Yeah, so it's a very natural measure on matrices that you can define. So imagine your matrix was filled with plus minuses. Plus was for ones and minuses for zeros, or vice versa. So you look at any matrix and you look at a submatrix of this. Yeah, and there's some distribution. So discrepancy of this submatrix is just the mass that this distribution places on the ones, the difference of that mass and whatever mass it places on the zeros. Yeah, the difference, the absolute value of this difference is the discrepancy. Yeah, of this submatrix. Yeah, with respect to this, and if you go over all of these submatrices, the max of that is the discrepancy. Okay. Now here's a very interesting conjecture. Yeah, which we can now formulate because of this correspondence. Take any function f, look at its matrix mf, which is this communication matrix. Yeah, and now I can define the discrepancy of that in just the way that I said before. Yeah, is it true? Now, suppose the discrepancy is very small. The smaller the discrepancy, if you go there, the smaller the discrepancy, what does it mean? This matrix looks, if you look at a random matrix, the random matrix will be completely plus minuses equally mixed. So if you look at any large submatrix, it'll have equal amounts of pluses and minuses, right? So the smaller the discrepancy, the more random looking a matrix is, right? So, and therefore harder that matrix is, right? So if the discrepancy of this matrix is small, then the conjecture is that if I look at p to the f, now that's a polynomial by our manufacturing process of polynomial, it's a set multilinear polynomial. The conjecture is that computing this polynomial is going to be hard for multilinear circuits. The size of the circuit that you need, a multilinear circuit, is 1 over the discrepancy. So if the discrepancy is exponentially small, then the circuit size that will be needed according to this conjecture is going to be exponential. Okay. Now, this is a conjecture that I must admit we haven't thought about much. This has just appeared in a recent work with, again, Rajit Datto, Utsav Ghoshal and Partho Mukhopadhyay. It is out on the archive. You can look at that. It's a special case of this conjecture. That conjecture is more general because there's a more general correspondence to discrepancy measures, discrepancy and arithmetic circuits. And this is a very special case of that conjecture. But I think it's an interesting conjecture because, there are lots of matrices for which we can prove lower bounds on discrepancy, very strong lower bounds. And, this says any such matrix, if it's hard, the analogous polynomial should be hard for multilinear computation. And this will be very interesting if you can prove it or disprove it, because if you prove it, this will give you the first super polynomial lower bound on set multilinear circuits. Yeah, there are none. Even for set multilinear circuits, there are none. This will be a major result. So this conjecture, if it is true, it will resolve a major question. If it is not true, you will find new cancellations, which will be already interesting. Okay, and now let me sum up by just saying that there are many open problems, including the conjecture, that sort of arise from this work? Well, one of the things was, as Siddharth was asking, can we improve this bound that we showed the exponential separation to all the way to 2 to the omega n? Is that even possible? I don't know. The second question is the Boolean analog. This is, there's this types of theorem called Aitai-Gurevich. I mean, these are very important questions that have been explored before. We don't know the analogs of this result in the Boolean world, meaning is there a constant depth? Is there a monotone Boolean function which can be computed by constant depth Boolean circuits using negations and cancellations, but that cannot be computed by monotone Boolean circuits in polynomial size? None is known. Okay. It would be also interesting to resolve the multi-partition log-rank conjecture. As far as I know, the multi-partition log-rank conjecture, which I talked about, is incomparable to the ordinary log-rank conjecture. Yeah, and this has a close connection. I can talk more about it after my talk. In the powers of multilinear computation and monotone computation for 0-1 polynomials. We don't know of any separation. And finally, it will be interesting to resolve the multilinear discrepancy conjecture that I just talked about in the last slide. And notice that, actually if you resolve the multi-partition log-rank conjecture positively, then that would also resolve the conjecture that I talk about in 4. Okay. Thanks a lot for listening to me, and sorry really for going over time. Thank you.
Yeah, so let's thank the speaker for the amazing talk and open the floor for questions.
Hey, quick question. So the discrepancy conjecture that you mentioned, that's for what measure, or doesn't matter?
Okay, so I did a mistake of. Can you still see my screen?
I think I see your screen. Yes, not the slides, but yeah.
Yeah, and the funny thing is, I don't see my screen. I don't know. Okay, let me do something. Let me stop sharing, and then again I'll share.
Cross button. Yeah.
Yeah. So they should stop sharing, and this will give me back my screen, I suppose. And now let me share again. Sorry for this. I've been having trouble with Windows. Yeah. Okay. So let's
see it again. Yeah.
You see it again, right? So full screen
mode.
Yes. Yeah. So you want to go back to the discrepancy conjecture, right?
Yeah. So the definition had a measure mu, but the conjecture does not.
Okay. Yeah. So for now, let's assume that mu is uniform. I mean, I would be interested to show for any mu actually. Yeah? Okay. I don't know, but certainly suppose mu is uniform. The mu is the uniform probability distribution, right? And the discrepancy is small. I mean, we have tons of matrices which have this property. Okay.
Right.
Explicit ones. Okay. Yeah. So manufacturing these matrices is no problem. Explicit ones, yeah. But we don't know whether. I mean, this is I mean, we still don't know how to get a good handle on multilinear circuit. But my hope is that by focusing on this conjecture, I don't think before our work there was a conscious effort made in relating discrepancy, the measure of discrepancy, with multilinear computation. And my hope is that once a conjecture has been put up, either it will be refuted, which will show us new interesting powers of multilinear cancellations, and help us refine. I mean, this would be very interesting. Or you will be able to, look at the right way at multilinear computations. It will be remarkable if, multilinear computations cannot compute such p to the f's. There's got to be something, right? That's not letting multilinear computations.
And is there a complementary upper bound? So if I give you a function f such that the mf has, say, high enough discrepancy, then so I'm wondering about the other, like an upper bound on s as a function of.
Yeah, I mean, if I give you a MF which is easy, meaning has high discrepancy, can you now compute it by? No.
Right.
No, I don't know of one.
Okay, so
I don't know of one. What is true? In some sense, there will be an upper bound in the product decomposition. Remember, there was this thing that we made a passage. I didn't prove it to you. I attributed Hayafield's name. Given an efficient computation by a circuit, we said there exists a decomposition, right? So you can find decompositions. Okay. Whether that decompositions will give you circuits, that's not.
Okay. Okay. A bit, yeah, makes sense. Thanks. Yeah, very nice talk.
Thank you. Any other questions? So since I can't see you, maybe I should stop sharing my slide. Sorry for going overboard and taking away your time.
No, I think, yeah, this is, yeah, it's not very strictly monitored.
I took that liberty.
Okay. So if there are no more questions, let's again thank the speaker, and maybe we can stop the recording and end.
Thank you for having me.